Contrary to what it says about eHarmony.com, which evaluates on 29 different dimensions of compatibility, whatever that means. Okay? There's no way a computer can tell if two people are going to be falling in love either. But those are subjective questions, those are human nature, and that's screwed up forever anyway, so we'll never get that straight either. But there are some mathematical, objective questions that a computer cannot solve. One of them is called the halting problem. Okay? And a computer cannot solve that no matter what. Okay, and that's a shocking thing. Language paradoxes, paradox of vagueness, some quantum theory, all these Hilbert's 10 problems, another thing that computers can do, and much more. So this has a lot of stuff. But, okay. Just want to talk about one thing. So we talked about these things, and now the traveling salesman problem came to light. I mean, people knew about it beforehand and they couldn't solve it, but it came to light really in the 60s. Chaos theories in the 60s. Relativity theory, 1905. Galois theory, 1832. That's when he wrote his letter. But it took about 100 years till people really understood what the letter was about and to get group theory on its feet and to show what it was about. Gödel's theorem, 1932. Okay? So these theorems are not, these ideas, these limitations are not old. These are very new, and they're coming out. Okay, type of theories. The traveling salesman problem. It's not that it can't be solved. We can write a computer that can do it. It's just impractical time-wise. Chaos theory. Impractical information-wise. If I was able to keep track of every single butterfly in Brazil, I'd be able to predict the weather in Texas. It's a joke, but you know, it's just we can't. It's just too much things going on. Relativity theory. It's not a limitation. It's just counterintuitive. Things don't have set distance or set time. Okay? There's no such thing as absolute time and absolute space. Things depend on what you're doing. It's a counterintuitive thing. What can be done by certain operations?
Any questions?
About the unprovability of certain statements, but I have two questions actually. Is there a way, or does there exist, or has anybody actually done any work into figuring out if there are certain classifications, if maybe a small amount of statements that you can look at before attempting to prove them, whether or not they're unprovable? And my second question is, under what definition of a set would it be possible to assume that set theory is consistent?
Well, let me do the first one. Yes, there are. Okay, so you can talk about something called sigma 1 sentences and pi 1 sentences, and there are certain sub-classifications in which they are, and you can look at these. You can look at a sentence and say, "Oh, this is definitely provable." However, it doesn't go the other way around. Just because something is not in it doesn't mean you can't prove it. So, because if you were, then you'd be able to if you would say, okay, he's a pi 3 sentence and all pi 3 sentences can be proven, then what did you just prove? You proved that this sentence can't be proved. So then you proved the sentence. So you can't do that. So there's partial answers to that. There are small things of mathematics which we can say, oh, this is provable. Now the second thing is, okay, ZFC, set theory, is consistent, but you have to assume something else. You have to assume something, you know, about large cardinals or something like that. Oh, okay, so, but question, is that system consistent? Well, you have to go up and go further. So, you have these systems within systems within systems within systems. So arithmetic is kind of inside, and then you have set theory, and then you have set theory with some axioms of large cardinals, and then you have larger cardinals, and things like that. It's tortoises all the way down. It's not stable.
Any other questions?
I see you're in the process of still writing your book. How will I know? I want to know when it's out so I can get it.
Me too. Find me a publisher. I didn't start looking for a publisher. I'm waiting to finish, but I should finish by the end of the summer. Okay. And then I'm going to find a publisher. Otherwise.
I don't want you to start with another story, but I think I have a friend who is very interested in Zeno's paradox. So I want to know your opinion about this paradox. Yeah, that's the first question. Second question I'll ask you later.
But it's an amazing thing. I got into it last summer to write about it, and it's just amazing. The thing's been around for 2,500 years, and no one has an answer. And basically, what he does is deny motion. Okay, and motion's impossible, time's impossible. I have no take on it. So there's a solution to Zeno's paradox, namely space is discrete and time is discrete. Okay, if space is discrete and time is discrete, then there is a problem. And quantum theory would kind of like it that space is discrete and time is discrete. It doesn't look discrete, doesn't feel discrete. You know, I'm not. But then again, I go to movies all the time, and movies don't look discrete and either, but they are. Okay, so I have optical illusions going on, but movies aren't. I don't come to any quantum theory. There is a few papers that are written which say the following. Now that we understand Cantor, the difference between countable infinite and uncountable infinite, that for sure Zeno's paradox is solved. Okay, but I didn't understand it when I read this book. I didn't understand that.
Are there any problems that the computer can do that you think one day might be possible with quantum computation, given the problem that you stated before?
Right. So it's very interesting. There are a lot of NP complete problems. These are problems that are provably very, very hard. And then there's P. Those are the easy problems. Okay. And then there are three problems that are three problems that are NP, they're not known to be NP complete, and they're not known to be P. Okay? One of those problems is called factoring. And they found an algorithm, there is a quantum algorithm, in 1994, Peter Shor came up with an algorithm that does factoring in polynomial time. Okay? So that was a shocking thing. However, it's not an NP complete problem. So traveling salesman problem, even if we build a quantum computer, still won't be able to solve. Okay, so that was a shocking thing that went a little bit beyond P. P is what can be done in polynomial time, and Shor's algorithm for factoring went further. But other than that, no, not really. And by the way, there's not a lot of algorithms for quantum computers.
Anything else? Any other questions? And let's thank our speaker.